GALE was quite a find for me. 2007 and 8, we got together and founded Imprimis, and he's both an experienced electrical engineer. He has experience at XL, used to be NSP in Minnesota, both as an engineer and as a lawyer for the company. He's experienced in high-level risk management and insurance. That was another stint he had. So I hope you'll listen to him carefully as he defines a few things we're trying to figure out about high-priority things to actually have real products, and also some means of remediation of those risks. And as you listen, please keep in mind a couple of things. Whatever you do, wherever you are, try to help advance the cause of protecting our infrastructure. And lastly, the words of General George S. Patton, I hope you'll ponder these words: fill the unforgiving minute with 60 seconds of distance run. I'll leave you with GALE. Thank you.
Thank you very much, Chuck, for inviting us, and for all of your patience in being here. And thank each of you for advancing the ball in some way in this whole field to help protect our country. One of the ways that we are trying to advance the ball is with some new products and extensive modeling and testing. So with that, one of the first things we've heard from NERC is that one of the biggest risks to the grid is if there is grid instability caused by a GMD event because of half-cycle saturation on the transformers. And it could be a blackout, but some utilities have said to us, well, a blackout will happen before there's any damage to equipment. So let's take that as item number one. Here are some recent blackouts in the U.S., and you can see that the estimated cost from the U.S. government is in the billions of dollars to the customer. So I think the cost to the customer has been overlooked in each of these situations. Why is the blackout important? For another reason, all of these big power plants, you don't just turn the switch to start them. They have huge feed water pumps, emission control systems, coal handling systems that take an enormous amount of power. So you first have to start a bunch of other generators to even get the large generators going, and then a coal plant, it takes hours and hours for the boiler to heat up to be hot enough to even generate steam. So the 2003 Northeast blackout, obviously pretty real. Here's what NERC said about that, and here's why we believe that procedures will be inadequate as a way to control or to protect the grid. There are many, many variables that will occur, whether it's the strength of the storm, the direction of the storm, what generators are in service, out of service, purchases, sales, on and on, time of day, the load level, etc. And so utilities have said all of their operators need specific simulation training for the conditions, and if the conditions are different, the operators won't know what to do. Well, look what NERC said about the 2003 blackout, and it's essentially the exact same thing that they're going to say about a GMD event. Start from the bottom: inadequate training, inadequate anticipatory analysis, inadequate communication, inadequate voltage control. It'll be all the same reasons. And guess what will happen? The blackout will last for a long time. Here's a big item. And the utilities have not had the data, perhaps, to focus on this issue until now. Idaho National Labs tested for harmonic issues at the distribution level. The utilities have been focusing on the high voltage level. At the distribution level, you get 33% harmonics at about 100 to 120 amps of current in the neutral. Well, the standard, IEEE standard, is 5%, 7.5% for a short period of time. That's going to cause damage to equipment, to motors, to rotors, to condensers, et cetera, et cetera. Louis Marti from Hydro One came out with an IEEE paper that said you're going to have damage to rotors, generator rotors, if you have more than 50 amps of current per phase. We're going to talk about, when we are designing equipment, we look at what the maximum credible threat is in order to come up with a design standard. what is some of the maximum credible threats? Data was filed for the Chester, Maine substation, thanks to what's going on in Maine. So for 20 years, they recorded the GIC, the ground-induced current in the neutral of transformers at that substation. John Kappelman correlated that data with magnetometer data from one of the nearest sources of a magnetometer. When you correlate that and put it together, and just look at the bottom line, because we got to go quickly here. If you look at where there's 100 amps in the neutral, this position down here, you see that's at about 250 nanotesla per minute. So if you ramp that up to 5,000 nanotesla per minute for a 100-year storm, you multiply that by 20. You're going to get 2,000 amps in the neutral. Remember what we were talking about for harmonics at only 100 amps. And remember what Louis Marti just said, you'll have damage to rotors at 50 amps in the neutral. So we're suggesting this is a pretty serious issue. You've seen this before, the coronal mass ejection, the size of it compared to Jupiter, compared to the Earth. What does it do? Look what it does to transformers on the bottom two pictures. The left one was in South Africa, the right one was Salem, New Jersey. And you can see once again the size of some of that. When we've done modeling, we've done extensive modeling with PowerWorld. PowerWorld was originated by Professor Tom Overby from the University of Illinois. So he's been able to simulate and put GIC currents on load flows to simulate what happens when there's a solar event while the grid is in operation. And by the way, John Kappelman has some modeling, Siemens now does, GE now does, Mitsubishi, etc. This didn't exist a year or two ago. So here are two individuals that have done an estimation of what the field will be for a 100-year event. At the top, John Kappelman's numbers are about 15.2 volts per kilometer, and there's 20 volts per kilometer on average for Ani Polkanen from Catholic University, although he's got a range of 10 to 50. So we simulated putting current blocking devices in the grid in Wisconsin, and we have a partnership that we're working with ATC in Wisconsin, so they've given us actual transformer and line data and so forth, and so we did this. And you can see what happens the more blockers you put in. This is only 25. You can see the total GIC. You can see the total GIC going down in the system, and you can see the megavar loss going down. For a while, the utilities didn't have the software tools to say, well, I don't think the grid will even go down. Well, here we are, and you can see here that with no blocking devices, the Wisconsin grid will collapse at about the 100-year level for a solar storm. And then as we start adding blocking devices, you can see the grid becomes more and more resilient. And this is out of a total of 350 transformers, and this is blocking only 27. So what we're saying is by blocking 10%, 15, 20%, you get significant resiliency in the grid, and it's not an overwhelming, huge, costly issue. Here's another really interesting graph. Remember before I said actual data could point to 2,000 amps of current in the neutral. So we simulated with PowerWorld over in Wisconsin. We said, what's the effect on the neighboring utilities if we blocked Wisconsin? Because we've heard from many utilities, oh, well, if we block, it'll push it to the neighboring utilities. Or vice versa, it doesn't do us any good to block until all the neighboring utilities do. Well, let's take a look at that. We'll call this a myth buster. So if you look at here, This is before there's any blocking. We took the 6 highest interconnections from the Wisconsin grid to the surrounding states. But look at here how high the current is on some of these. Here it's almost 3,000 amps. So under a simulation, it is confirming what the actual data could be. And then of course there's 2,000, 1,500, 1,000, etc. And when we put blocking in Wisconsin, look what happens. These lines, virtually nothing happens. Now the reason it doesn't go down is we're not putting blocking in the neighboring states. But if you look at that, it completely debunks the myth of we're going to add current to the surrounding states or vice versa. So there's no reason a state shouldn't go ahead immediately and do blocking. They will not adversely impact their neighbors. This was the system that we started out with and is still offered for sale, which is basically here you have the solid ground connection, and during GIC it goes through a resistor and a capacitor bank. That doesn't allow the DC current to go through, but the AC does. That's been tested. It's been simulated at the University of Manitoba. It's been tested at Kima Labs in Philadelphia, and of course Idaho National Lab that was talked about this morning. It was placed into a high voltage grid and it operated just fine. In fact, here's a kind of a synopsis. These lines over here are with no blocking. So when there's current injection, DC current injection of different levels, you can see that here. That's what the curve would look like. But as soon as blocking was put in, and it was arbitrarily set at different time limits here, it immediately went to 0 in every case where it was set and goes across. So it just stops the block, it stops that altogether. Our guys were out at the site, and when they were injecting DC, the transformer would be humming and shaking and noisy, and as soon as the blocking went in, it stopped, just like that. So we've come up with an even beefier system. When we did some testing, we found, in modeling, we found that in the Wisconsin grid, at the 100-year storm level, we checked the voltage level at every single substation, and with one exception, the highest that it was at was 2,000 volts. The first, the first model that we had was capable of operating at 4,000 volts, but there was a one long line, a 150-kilometer line. So 150 times 20 volts is 3,000 volts, and so we said, you know, for long lines in other states, maybe even for 30 volts per kilometer, let's make a beefier unit. So we did that with 2 capacitor banks, and it's now 8,000. So it's 8 kV, which will handle, we think, virtually any situation. If there happens to be an extra long line for EMP at 50 volts per kilometer, we can add more capacitor banks and it'll still operate. We also have a thyristor bank, which some utilities were saying, well, what happens if I have multiple faults during a GMD event? Very unlikely, very, very, very unlikely. But we said, okay, we'll deal with it. And so we put in a thyristor bank, so this can fire repeatedly so that a fault will not destroy or take out the capacitors that are put there for protection. So here's the upgraded model, and you can see that it's got 2 capacitor banks here at the top, so the size of it hasn't changed. It's still 8 feet by 8 feet. We just pushed everything and got it closer. We use SEL Electronics Schweitzer. We had electronics made by a California firm that worked just fine, but we said, you know, for the confidence of the utility industry, we're going to use a proven gold standard, if you will, and so we've entered into a further partnership with Schweitzer Electronics and, of course, ABB parts. I'm not going to go into all of this, we don't have time for it, but we're demonstrating to the utilities that there is substantial backup and redundancy with every component and so forth, so they don't ever have to worry about not having an effective ground as defined by the code. As a quick example to that, it's solid ground. The utilities most of the time want to operate in solid ground. But an effective ground under the code is still to operate through a power resistor and capacitor banks. This technology was developed by utilities, quite frankly, in 1983, 30 years ago. But they only had this. They didn't have the advancement of solid-state electronics, which now allows us to keep it in a solid ground 99% of the time and then switch over to this only when it's needed. So we're trying to satisfy the issues that utilities have. We did a study here as to any unintended consequences. If you get a bunch of these installed in the grid, is it somehow going to affect the operation of the grid? The University of Manitoba in short order said, no, no problem. EPRI, the Electric Power Research Institute, has also just studied that and said, no problem. This is Schweitzer installing the unit over in the ATC grid in Wisconsin. The cost for this ranges, if you buy them one at a time, probably as high as $320,000, and the installation is $25 to $50. Utilities now, when there's a solar storm warning, PJM as an example does it on the East Coast, Con Ed, Dominion, they redispatch energy, meaning they back down baseload generation and they start a bunch of peaking units so they have bar generating capability. Instead of having 2 trucks running at their engines at full speed in the parking lot, they want to back the trucks down and have 20 cars starting and running at it. But the problem with that is the cost of the energy is much higher, and that that cost is passed on to you. That cost in 1 to 2 years could pay for remediation of the whole grid. So just to put this in perspective. We also think that when transformers are humming and shaking and all these things are going on, or you get 1,000 amps or 3,000 amps in the neutral, we think that blocking can certainly save the life or extend the life of a transformer. The average age of transformers today is 42 years. So you put that in perspective, we're talking about an old fleet to begin with. One of the ways that we are trying to advance the ball is with some new products and extensive modeling and testing. So with that, one of the first things we've heard from NERC is that one of the biggest risks to the grid is if there is grid instability caused by a GMD event because of half-cycle saturation on the transformers. And it could be a blackout, but some utilities have said to us, well, a blackout will happen before there's any damage to equipment. So let's take that as item number 1. Here are some recent blackouts in the U.S., and you can see that the estimated cost from the U.S. government is in the billions of dollars to the customer. So I think the cost to the customer has been overlooked in each of these situations. Why is the blackout important? For another reason, all of these big power plants, you don't just turn the switch to start them. They have huge feed water pumps, emission control systems, coal handling systems that take an enormous amount.
And also some means of remediation of those risks. And as you listen, please keep in mind a couple of things. Whatever you do, wherever you are, try to help advance the cause of protecting our infrastructure. And lastly, the words General George S. Patton, I hope you'll ponder these words, fill the unforgiving minute with 60 seconds of distance run. I'll leave you with Gale. Thank you.
Thank you very much, Chuck, for inviting us and for all of your patience in being here. and thank each of you for advancing the ball in some way in this whole field to help protect our country.
GALE was quite a find for me. 2007 and 8, we got together and founded Imprimis, and he's both an experienced electrical engineer. He has experience at XL, used to be NSP in Minnesota, both as an engineer and as a lawyer for the company. He's experienced in high-level risk management and insurance. That was another stint he had. So I hope you'll listen to him carefully as he defines a few things we're trying to figure out about high-priority things to actually have real products.
Amount of power. So you first have to start a bunch of other generators to even get the large generators going, and then a coal plant, it takes hours and hours for the boiler to heat up to be hot enough to even generate steam. So the 2003 Northeast blackout, obviously pretty real. Here's what NERC said about that, and here's why we believe that procedures will be inadequate as a way to control or to protect the grid. There are many